Hi, we have been discussing about multiple linear regression, and this is the example we have used, right? A software firm collected data on sample of 20 computer programmers, and we have the two independent variable, which is years of experience and the score on the firm's programmer aptitude test. Whether these two things affects your dependent variable salary was what we are testing, and the years of experience, score on the aptitude test and the corresponding annual salary for them is given in the data set something like this, right. So, this is a snapshot of the data set. So, we have a sample of n is equal to 20. If you recollect, so these are the things we have done, and then we have run a regression and then we interpret the coefficients. So, now moving on, we are going to go for whether whatever the model we have built, that is a regression model we have built, is good, whether it is model fit is good in 4 criteria. That is what we are going to see under the topic model diagnostics. There are essentially 4 diagnostics that we do for any multiple linear regression model. The first one is coefficient of determination, called as R squared, and in terms of multiple linear regression we call it as multiple coefficient of determination, but anyway we always refer to them as R square. The second one is whether the regression coefficients, whatever the independent variables we have used, which of the independent variables are significant or not, that is what we will test. That is basically hypothesis test for regression coefficients. Then whether the model is overall fit, that we get it as overall model fit, that we do using analysis of variance. And the last but not the least, which is very important, we call it as a residual analysis to validate the regression model assumptions. There are certain assumptions we have taken before we build the regression model. So, those assumptions has to be validated after building the model. Then only we can declare that whatever the estimated model is perfectly fit and it can be implemented or deployed. Moving on. First we will discuss about multiple coefficient of determination, called as R square. Basically R square gives you a relationship between what is called as sum of squares of total, sum of squares of regression and sum of squares of error, right. As we have seen before, total variance is represented as sum of squares of error, right. Total variance in the regression model is explained by sum of squares of regression, which we call it as explained variance, and sum of squares of error, which we call it as unexplained variance, right. So, if you recollect the regression model, let us say y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus so on and so forth plus beta k xk plus the error term, right. So, this is the total variance. If you look at it, SST is composed of the regression variance, which is your explained part, sum of squares of regression, plus the error term part, which is sum of squares of error, right. So, now what do we want? We want sum of squares of regression to be more and sum of squares of error to be less, right. So, that is accounted by R square, which is equal to relationship between SST, SSR and SSC, that is sum of squares of regression, that is explained variance, divided by the total variance. So, higher is the better. Right. So, R square ranges between 0 to 1, right. In terms of percentage also we call it, let us say for example, if the R square is 0.89, we call it as 89%, right. This is basically your coefficient of determination. That means 89% of the variance in the dependent variable is being accounted by the independent variables. So, that is the idea that we need to take into account. Now, moving on, ideally what is the relationship between SST, SSR, SSC we found out, but in terms of notation this is how we have got it. So, we have yi, which is your observed variable, which we get from the sample, right. So, this we get from the sample data, and then the y hat is your predicted value, and y bar is the average value. So, multiple coefficient of determination is interplay of these things, right. So, SST is nothing but if you look at it in a regression. So, let us say these are the sample data, right. So, these are sample data, we try to fit a best fit line, and if at all we could not able to fit the best fit line, ideally we go for taking an average. So, this is your average. So, say for example, this is your y bar and all these dots are your yi's, and this is basically your predicted value, that is y hat. So, SST is nothing but yi, that is the sample value minus y bar, right. So, that explains your total variance is composed of sum of squares of regression. Sum of squares of regression is nothing but the predicted value minus the average value, and sum of squares of error. What is error? So, this is the actual value and this is the regression line, right. So, the distance between the actual value and the regression line is basically referred as error, right. So, we do this interplay of squares between this and then we reach to the coefficient of determination, and this is the ANOVA output, right. So, from which we can calculate the multiple coefficient of determination. I think by now you are prevalent with accustomed with the ANOVA table. So, this is the sum of squares of regression column, which is your C column, and let us say this is your SSR, this is your SSE, and this is your SST, right. So, now R square is given by SSR divided by SST. So, SSR is this 500.33, let us say, and SST is 599.79. Then putting plugging in the values, right, SSR and SST, we get the value of 0.83. So, that means what? 83.42% of variation in the dependent variable is accounted by independent variables, right. So, that is quite high, that means we can say that it is a good predicted model, right. So, model diagnostics first step is successful and we can be happy about it. And there is one more concept called adjusted multiple coefficient of determination, right. So, R square is basically the multiple coefficient of determination. Adjusted multiple coefficient, we call it as adjusted R square, right. So, what is the need for adjusted R square? So often than not, what happens if a researcher keeps increasing the independent variables, it can inflate the R square value. That means, if there are only 4 independent variables and possibly let us say hypothetical situation R square is 0.84. If I add one more independent variable, right, so plus 1, so that means 5 independent variable, essentially the independent variable that you are adding contribute to some explanation part in the dependent variable, and hence the R square will eventually increase, right. So, 86. So, sometimes people play this trick of increasing the R square because higher R square means better explanation, and hence they keep on adding the independent variables even though it may not be significant, right. So, in order to control that, statisticians have come out with something called as adjusted R square. So, what does adjusted R square does? Adjusted R square penalizes for additional independent variable, right. If at all you are adding an independent variable which is not significantly affecting the dependent variable variation, then it will penalizes the R square. So, that means it will bring down the R square. So, usually people prefer comparing with R square and adjusted R square. Adjusted R square gives a realistic picture. R square might tend to be getting inflated depending upon the independent variable. The formula goes like this. So, obviously the R square cannot be more than 1, that is 1 represents 100% variation. So, if you look at this, the formula is 1 minus R square, which is basically coefficient of determination, and n minus 1 divided by n minus p minus 1, where p is the number of independent variables here, right. So, as you can see, the independent variable n minus p is in the denominator. So, that means every increase in independent variable which actually decreases the R square value, right. So, that is why adjusted R square, right. So, if you no regression better, adjusted R square will always be less than the actual R squared, and statisticians prefer to go with adjusted R square because sometimes researchers tend to get moved and then want to inflate the R square, and hence they keep adding the independent variables. In order to control that, we go for adjusted R square. So, this is one of the concept that you need to understand. So, next time when somebody shows you the regression output, so instead of R square and adjusted R square you should go for, because that gives a realistic picture, whereas R squared gives a optimistic picture. Now, moving on, for this is a calculation involved in it, right. So, let us just have a look at the calculation. So, this is your 83.42 for the R square. Now, substituting the respective values. So, n as you know is 20 is a sample size, and p is the number of independent variables, which is equal to 2, right, and then substituting the respective value you get 81.46, whereas R square here in this case itself you can take R square is 0.8342, and whereas adjusted R square is 0.8147, right. So, of course, there is a nearly 2% decrease in R squared. So, that essentially gives a correct picture about how much of the variation in the dependent variable is being explained by the independent variable.